Ever since Darwin, biologists have understood the importance of the tree of life metaphor. In PhyloMeth, we will learn how to infer that tree and how to use it to understand biological processes. PhyloMeth is made possible through a career grant from NSF, as well as ongoing support from the University of Tennessee, Knoxville. So today I want you to learn about tree search and why it might be hard, right? And so you think, okay, we're going to get these phylogenetic trees, that's great. Is it an easy or hard problem? I just want to get an intuitive sense that it's a really hard problem. We have very clever computer programs that help us do it efficiently. You should be somewhat terrified of the scale of the problem to start with. Okay, it's healthy. So I want you to understand why there are so many trees and understand why tree search is a difficult problem. So let's take a simple two-taxon tree, right? There's only one two-taxon tree that's rooted, okay? You might think, what about this tree, with B on the left? It's just a rotation of that initial tree, right? And if you're unclear about this, you can look at the Reading Trees video to understand more about this, okay? So with two taxa, I have just one tree. If I want to add a third taxon tree, C, where could it go, right? Well, it could go on this branch leading to A, and so I get this tree out. It could go on the branch leading to B, and I get this tree out. Or it could go on the branch below A and B on a rooted tree and get this tree out. Right? So I've gone from one tree to three trees. Okay. What about the next step? What if I want to add a fourth taxon? Right? Where could that go? Well, that could go on this middle tree to any of these branches. Right? And on the left tree and the right tree, it could also go on any of those 5 branches. And so that results in 5 for each of those trees, so 5 times 3, 15. Okay, so for 4 taxa, there are 15 possible bifurcating rooted trees. And we continue this, right? So 2 taxa, 1 tree, 3 taxa, 3 trees, 4, 15, 5, it's 105, n, it's this double factorial, right? So 3 times 5 times 7 times 11, so forth. Okay, this gets big very fast. Okay, and compared to exponential growth, right? So we see a movie, oh no, the Borg are increasing exponentially or something like that. That's scary. Tree growth is even faster, right? So here we see a doubling each step. Okay, here we see increasing tenfold each step, and here we see the number of trees, how they increase each step. Okay, and even if you compare it to increasing tenfold each step, eventually it surpasses it, right? And even for 10 taxa, there are already over 34 million possible trees. Okay, here we see on a log plot, right, where n versus exponential growth and this factorial growth that tree space goes through, right? And so the number of atoms in the universe is about 10 to the 80, right? And by the time you get to 52 or so taxa, there just aren't enough atoms as there is for trees, right? So I wanted to write down every tree I looked at, and for tree space, I'm just out of atoms to do it in, even if it's sort of 1 tree per atom. Okay, and that's just for 50 or so taxa, right? We have a million species on the planet, well more than a million species, in fact. Right, so I have a tree of all life, which is the goal for many of us, right? The size of that tree space is just tremendous, right? This huge, huge thing. I try to find the one best tree out of that huge space. Okay, that's a hard problem. So how do we do this? Well, we do it based on a tree search, right? And some of these tree search is like finding your favorite in a box of chocolates, except the box is very, very large, right? And how do you find your favorite chocolate, right? Well, if you look at visually at appearance, okay, maybe this looks good, that looks bad, right? But with this sort of thing, you have to actually taste it, right? Maybe this is dark chocolate, maybe this is mint, maybe you hate mint, right? Maybe this one has a cherry inside secretly, right? And so to search over this space, you would pick one up, bite it, see if you like it, go on to the next one. Right? You might start being able to group some by similarity, right? Maybe I think that the ones that have sprinkles on top just always taste bad. I can throw those out, right? But it could be that there's a particular combination of sprinkles that you just love, right? But if you just do that heuristic to throw out the ones that have sprinkles, you might miss it, okay? And so tree search is very similar to this, right? No matter whether you're using parsimony or a Bayesian approach or likelihood, you have to pick up a tree, look at it, and then calculate something on it. Its parsimony score, the probability of data evolving on that tree, or so forth. And that step takes a while. And so what you do is move across this tree space, sampling them. But when tree space is so huge, it's very hard to find the right one. Okay. This relates to a set of problems called NP-complete or NP-hard problems in computer science. right? Here from Randall Munroe is a great cartoon about this, right? And so similar to this tree search problem. Imagine you go into a restaurant and you have a list of appetizers and you say to the waiter, well, like exactly $15.05 worth of appetizers, right? If the waiter said to you, okay, that'll be 15 sampler plates, you can look at it and say, nope, that's not right. Right? It's easy to find that answer is wrong. If you said 7 mixed fruits, you could look at it and say, oh, yeah, actually that works, right? And so you can verify these solutions or reject these solutions very quickly. But if you were to find out there's actually another solution here rather than the mixed fruit 7, to try to find that is very hard, right? You could try, let's try 2 mixed fruit and 3 French fries. Let's try 1 mixed fruit and 15 hot wings, and so forth. There's a huge space of possibilities, much like tree space. Okay, and like tree space, if I said to you, here's a tree, calculate its score, you could do that very quickly. If I were to say, is there a tree that has a score, 1 change fewer than that tree? That would be a very hard problem to solve. Okay, and that's the sort of problem we try to solve in phylogenetics over this ginormous space. Okay, to give you a concrete example, so Smith et al. Back in 2009 inferred a tree of 13,533 species, and so of land plants, right? Now, imagine someone came in and said, oh, what about these 2 species you missed? Could you please add them to your tree? How much bigger is the tree space to search over then, created by those just 2 species, right? And again, think about how fast this grows, right? So if we think of the original search space as something like the size of a university campus, right, and trying to find some object, say a rubber duck on a campus, that's a hard problem, right? Adding two more taxa increases the scale of the problem so much as then the area of the planet, right? So somewhere on the globe there's a rubber duck, go find it, rather than somewhere on this campus is a rubber duck, go find it. Both problems are hard. The one on the right's much, much harder, right? And so it gives you a sense of how fast this tree space grows and how hard the problem is that we set ourselves to finding the best tree. Okay, and once you're at the point of having, 10 to the 80, 10 to the 300 trees, the odds of you getting exactly the right one are trivial, right? There's no way you have enough precision to get that, right? So any tree you're going to get has some errors on it somewhere. And we'll talk about ways to figure out what those errors are. There's a greatest uncertainty, but we hope that with enough data, we start to narrow in on the parts of the tree we really care about that are right. Angiosperms are clade, birds are clade. We figure those things out from phylogenetics and with high support. Okay, so summary for this: there are many, many trees. Finding the right one is a very difficult problem. We'll talk later in the course about how we go about trying to solve that.